Okay, let's consider an old incandescent light bulb. So we've got an old incandescent light bulb here, and it screws in, and we've got a tungsten filament in here. So the filament is made of tungsten. Chemical symbol W. And so it's basically a resistive wire. Now, when the light bulb heats up, it's going to be white hot, glowing. Okay, so when it's operating, the temperature when it's operating is going to be about 1800 degrees Celsius. And we're going to say that this is rated as a 60-watt light bulb. Again, we're going to do an old-fashioned incandescent bulb, one that just glows because it's hot, not an LED, not a compact fluorescent or anything like that, just an old-fashioned incandescent bulb. And so the question is, how much current was that bulb pull when you first turn it on if you assume that the initial temperature before it gets hot is 20 degrees Celsius? So I want to know how much current does it pull at the beginning. So now this is an incandescent bulb that normally plugs into a 120 volt outlet. Okay, so these are the basic parameters. So normally it's 120 volts. This is your generic household voltage. When the bulb is on, it's rated as 60 watts at 120 volts. The operating temperature is 1800 degrees. So we have to work backwards, and we say when it's on, it's hot. Okay, 1800 degrees. We know that it's 60 watts at 120 volts. Well, that means this is the power that is dissipating. Conservation of energy. Power dissipated equals power supplied. Okay, so the power supplied is going to be current times voltage. Okay, now we're going to ignore the whole fact that your household wiring is AC, and this is really we're talking about DC stuff right here. So we're just going to pretend it's all DC because we'll talk about AC current, AC power later on in the semester. Okay, so I times V. So that means that I is going to be P over V. So that'll be 60 watts divided by 120 volts. In other words, half an amp. So it's pulling half an amp when it's on. So this is when it's hot. It's pulling half an amp. So that means that we can find the resistance here. V equals IR. So that means R is V over I. So the resistance when it's on is 120 volts divided by half an amp. So that's going to be 240 ohms. So this is the resistance of the bulb when it's operating, but it's hot. We know that resistance changes with temperature. So I want to know, what was it when it was cold? So we know that the resistance changes. It's equal to R naught 1 plus alpha delta T. Okay, so we need to know alpha for tungsten. Again, this is something you can look up. I mean, you either memorize the physical properties of every known substance or you learn where to look things up. Your book has a table where all these values are given for you. So it says 10 to the minus 3 inverse Kelvin. Well, that inverse Kelvin is also the same as inverse Celsius degree, because the Kelvin and Celsius degree scales have the same spacing. So that means it's the same for both of those. Okay, so what is delta T? Okay, well, delta T is going to be the difference between the 1800 degrees Celsius, which is the temperature while it's operating. So the temperature while operating minus the 20 degrees Celsius, which is the initial temperature right there. Okay, when you first turn it on. So that's going to be 1780 degrees Celsius. Now all we have to do is do algebra to our equation up here to solve for R naught. So R naught is going to be R divided by 1 plus alpha delta T. So R naught is going to be 240 ohms divided by 1 plus 4.5 times 10 to the minus 3 inverse degrees Celsius times 1780 degrees Celsius. And so R naught comes out to be 26.6 ohms. So even though it's 240 ohms when it's hot, when it's cold, it's only 26.6 ohms. So that means that when you first turn on the light switch, the current is going to be V over R. So when you first turn on the light switch, then that's going to be 120 volts divided by 26.6 ohms. And so that comes out to be 4.5 amps. So when you first turn on the light bulb, it's 4.5 amps, and it quickly, in a fraction of a second, reaches operating temperature, and so the current drastically drops. So current versus time, it starts off here and it drastically drops from 4.5 amps down to half an amp. Now, if you remember incandescent bulbs, you turn on the light switch, when do they most likely blow out? It's not when they've been sitting there for a long time, it's when you first turn them on. They flash and they burn out. And that's because when you first turn them on, that's when you have the biggest current load and the biggest power. Okay? Because now the next question is, what's the power being dissipated? You know, we know it's 60 watts when it's hot. Okay? So when it's cold, how much power is being dissipated? Well, that's I squared R. So that would be the 4.5 amps squared times 26.6 ohms. So that's going to be quite a lot more than when it's hot. And so that turns out to be about 540 watts. So even though it's a 60-watt light bulb, it's dissipating 540 watts for the first fraction of a second that you turn it on. And of course, this huge power loading in it is what actually damages the light bulb. So a light bulb that you turn on and off a lot is going to wear out and burn out a lot quicker than one that stays on for a long time.